Good afternoon, everyone, and welcome to today's webinar titled Report Interpretation, Particle Counts, Water Testing, and Ferrography. My name is Taylor Colon, and I am a Customer Engagement Specialist at TestOil. I'll be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure that high-quality recording is made. Second, feel free to ask questions in the questions box in the GoToWebinar application. We'd be happy to answer any questions that you have. Finally, the webinar recording will be distributed later today along with a survey. Look for that email in your email that you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. And just a little bit about Evan. Evan is a certified lubrication specialist with diplomas in chemical engineering. He's registered with CET and ASET. He's also OMA1, MLLT1, MLA2, CET certified. Evan has been a member of STLE for over 18 years and also serves as a senior tech advisor at TestOil. All right, Evan, if you're ready, I will pass the controls over to you.
Great, thank you, Taylor. So today's presentation is one of many webinars in a series. This one's going to focus on just a few tests. For those of you just joining us and not having taken part of the earlier series, I tried to explain that most testing can fall into one of three categories. Basically, you're either measuring fluid properties, contaminants, or wear, and this is sort of how they break out. As you can see, there are a couple of tests that branch into two categories and one test that covers all three. So today's webinar is focusing on a little bit of the contamination and in the wear debris section. As I explain each and every test, I will go over the scope and significance, generally quoting directly from the ASTM method so you understand what is the test supposed to be telling you and how is that relevant to the oil sample. After that, I'll give a brief explanation in layman's terms of the principle of the test, so that you understand how it's performed, which helps us understand what limitations and interferences the test may have. There are many times where a test can't tell you what possibly you think it will tell you, so I like to make sure that we clear that up. Also, where possible, I'll provide the precision and bias statements, again, usually directly from ASTM, so you understand just how far into the results you can interpret the data. You know, is it accurate to the nearest whole number? Is it accurate to one decimal place? That kind of thing. Once I finish explaining all the tests, I'll get into the results of the test and what is the most common reason, at least from my experience, that drives that value to go up or down, and what might it correlate with to help you confirm if that is in fact the mechanism at play. After that, I'll get into what I call exceptions, which are really the second, third, fourth most common reasons for that value to change. Once I've covered those off, the last thing I like to conclude with are the pitfalls. How do we misinterpret the number commonly, and what should we not do to misinterpret our data going forward? So saying that, I will begin with particle counting. Now, particle counting can be done one of two ways. So I'd like to describe optical first, and then I'll describe pore block second. Now, with optical particle counting, as you can see by the scope here, the idea is that it's supposed to count the concentration of particles in given size ranges. Now, the size ranges will vary from as low as 4 microns up to approximately 200 microns, and that is largely dependent on the instrument itself. The significance of particle counting is it gives us an overall view of how much contamination is present in the oil sample. It doesn't tell us what the contamination is, but at least it quantifies it to some degree. Now, saying this, the simple way of viewing an optical particle count is that we take a volume of oil and we flow it through what we call a cell. The cell is a 100 to 200 micron gap, and the oil sample is moving. On one side of the gap, we place a bright light source, usually equated to a laser. It's not quite a true laser beam, but it is a pretty powerful light. It is like a laser pointer in that regard. And that light source is pointed through the oil sample towards a photoreceptor, and the photoreceptor is not a whole lot different than the CCD sensor on a normal digital camera. What happens then, as the oil flows through this beam of light, it will create shadows. And so the CCD detector detects the shadows, and all it does is it sizes the shadows according to the area of the shadow. And this is the important thing to understand. So by counting and sizing the shadows, it has an idea as to how many and what size are the particles going by. The issue with the sizing and going by area is what we call spherical equivalency. If a particle goes by and it's 10 microns long and 1 micron wide, what the algorithms in the computer do is take that area and say, what is the largest circle, essentially a sphere, that would cast a shadow of that area. So a 10 micron by 1 micron particle goes by, it might get sized as 3 microns because a 3 micron diameter sphere would have the same area. So this is something we should always be aware of, that we're not measuring the shortest dimension, we're not measuring the longest dimension, we're not measuring the average dimension. We're measuring a spherical equivalency. Now with this test, one of the strongest limitations to any particle counting is it doesn't tell you what it is, just how much of it is present. And the other limitation based on the instrument is that it can't count particles smaller than 4 microns, that's based on calibration, and it can't count particles larger than 200 microns, which is essentially based on the size of the cell. A particle larger than 200 microns would not enter the cell and therefore could not be counted. Interferences to this method, however, are anything else that might cast a shadow, and that could be air bubbles, water molecules, or soft contaminants like varnish. So this test tends to skew high unless special steps have been taken to prepare the sample. If you send the sample through the instrument neat, meaning no dilution, no mixing with anything else, you tend to get a higher count than you would if you dilute the sample and then take the dilution into consideration. What a dilution helps do is, depending on the solvent that you use, it can negate the effects of water. It can help the water not separate out so readily, so it won't create any shadows based on its globules. And with a thinner overall sample, air bubbles are able to exit out of the sample a bit more readily, and we can accelerate this with other steps like pulling a vacuum on it or sonicating the sample. So understand that optical particle count does have a couple different sides to it in terms of interferences, and they can be overcome to some degree, but at the end of the day, it still hasn't really sized the particles according to their true size. The other method we have for doing particle counting is called pore block. Now, pore block is often referred to as flow decay because essentially the two terms are interrelated. What you do in this case is you flow the oil through a screen. Now, the screen is a calibrated screen with known pore sizes of holes. So what you do is you push the sample through at a constant pressure and you measure how much the flow decays. So based on the calibration of the screen, you can estimate then that the holes, the pores, will plug first with particles larger than the pores, and as that reduces the number of holes, you'll start collecting smaller and smaller particles on this particular screen. So with this test, we don't have any interferences due to water molecules, air bubbles, and soft contaminants. However, we are assuming the calibration is a fairly linear distribution of large and small particles. So again, we're not measuring directly all the particles and measuring them in any particular size fashion. We're estimating it based on a known calibration. So the limitation to this test is it's all extrapolated data, and the extrapolation is based on which size screen you use, and they're typically 5, 10, or 15 micron pore sizes in the screens. But as for interferences, this version of a particle count does not have any, which makes it a preferred type of particle count in particularly dirty situations, or if you know the sample may be heavily contaminated with water, or in samples that have relatively higher viscosities and air bubbles aren't as likely to come out of them. So in the more extreme cases, pore block becomes a very much a preferred method for doing particle count over optical. Optical is just more commonly performed in some commercial labs and certainly with on-site or portable testers. Now, regarding the precision and bias of this method, the data that's published here is based on the optical particle counting, and this is the ASTM method for it. And as you can see, it gives you repeatability and reproducibility data at 4, 6, and 14 microns. You'll notice that the reproducibility, which is sort of your go-to precision statement for sample-to-sample comparison taken at different days, we're talking around 100% or better error in the method. So the statement I underlined there is understand that that means at least a 1 ISO code difference between two samples taken from the exact same system, even 1 day apart, is pretty standard, but that may equate as high as up to 2 codes. So we can't get too bent out of shape if our particle count data fluctuates a little bit, as long as it stays overall within the same distribution and stays within 1 or 2 codes of where it normally sits. Now, talking about ISO codes, some people aren't that familiar with ISO codes in terms of how we look at the data. So let me just take a quick sidestep here. Let's try and understand ISO codes. So when we report the data from either particle counting method, we give the particle counts, which are a count per milliliter, in 3 different size ranges. Now the size ranges are 4 microns and up, 6 microns and up, and 14 microns and up. There's no upper limit to any of those 3 ranges. So what I want you to understand is that any particle counted as being greater than 14 microns will be counted again as being larger than 6 and larger than 4. So as such, the greater than 4 micron particle count is always the highest of the 3 values because it's counting everything. The 6 micron count has just a little bit less that it's counting, and the 14 micron, of course, even less again. So the order in which they're reported is 4, 6, and 14, so they go from highest to lowest. Now, these are the size ranges that we're reporting, but the results are coded. So how do we get the coding? The coding is provided by ISO. ISO 4406 is the standard for coding particle count results. And if you look at the table on the left, you can see the ISO codes down the left-hand column, and you can see the range in the next 2 columns to the right. So if you start 5th one from the bottom at an ISO code of 10, an ISO code of 10 refers to any particle count that yields a result between 5 and 10 particles per milliliter. If you go up to an ISO code of 11, it comes to 10 to 20. And if you go to 12, it becomes 20 to 40. And as you see, continuing the pattern, every time you go up 1 ISO code, the particle count will double. The range will get twice as large. So the ranges are ever increasing. So this factor of 2 is something we always must consider when reading our particle count results, that every time we see a result go up by 1 code across all 3 measurements, you've doubled the number of particles, relatively speaking. And every time we go down by 1 ISO code, we've essentially cut the particle count in half. Now, if we look at the top right table just for a second, there's an actual particle count being reported. So there's 151,773 particles greater than 4 microns. If you look over to your ISO codes, that equates to an ISO code of 24. The 6 micron particle count, as you can see, equates to a 22, and the 14 micron particle count equates to a 19. So you would report this set of values as a 24, 22, 19. The bottom right just gives another example at substantially lower results, and you can see how that one codes out. So as I always like to joke with particle counting, is that the ISO coding system takes one set of numbers that you don't understand, which is the particle count per milliliter, and converts it into another set of numbers you probably still don't really understand, but at least they're smaller. So let's try and understand an ISO code and see what we can make of the coding of results. So keeping the ISO code table to the left in mind, let's take a look at some actual results here. So we've got a first, second, and third sample. So let's start with the first sample. If I was to refer to the table on the previous slide and code these results, this is how it would shake out. 1,357 particles is between 1,300 and 2,500 particles, which is an ISO code of 18. 361 particles is between 320 and 640, which is the ISO code range for 16. And 42 is between 40 and 80, which is the ISO code range of 13. So that very first sample would code out as 18, 16, 13. Now if I move to the second sample and keep those size ranges in mind, you will find that that second sample also will code out to be 18, 16, 13. And in fact, if you were to do the third sample, you would discover all three of these work out to an ISO code of 18, 16, 13. So this is part of the reason that ISO decided to come up with this coding system with these broad ranges. When we look at these broad ranges, we can appreciate now that all three of those ISO particle counts are in fact within, as we call it, the same ballpark. So even though you see what looks like a substantial increase going from the first to the second to the third sample, in actuality, relatively speaking, they're all about the same. So we wouldn't get that excited about the changes that we're seeing here, and that's sort of the purpose of ISO coding, is to remove the resolution in terms of how far you read into the data. You don't read into those few hundred particles per milliliter changes as being actually that substantial at these levels. So I realize that probably now you're understanding particle counting a little bit better, but you're still thinking to yourself, I just don't understand what 18, 16, 13 would look like. How much is that? Is that a handful of dirt? Is it a bucket full of dirt? Just how much particulate are we talking about? Well, thankfully we have an interesting study from Caterpillar that we could reference. And Caterpillar took a drum, which means 55 gallons, 205 liters, of oil, and they found to contaminate that entire drum of oil to a level of 18, 16, 13, it only took a half a teaspoon of debris. So 1/2 teaspoon of particulate can take a drum from essentially no particle count all the way up to 18, 16, 13. So half a teaspoon doesn't seem like much, but 18, 16, 13 is often considered to be an upper limit in many different industrial systems, that they would not want the concentration any higher than that, and if it was a particle count higher than that, action would be required. So to help put this into perspective, understand this though. The average particle count in a new oil is somewhere around a 20, 19, 16, give or take an ISO code, which means that it's 2 or 3 codes higher than what we're looking at right now. So that would mean that if you take a half a teaspoon and double it to go up 1 ISO code, double it again to get up 2 ISO codes, that's 2 teaspoons of dirt or debris, particulate, that could be found in any drum of new oil and might possibly be higher, because if it happens to be 3 codes, then you double it again. Now we're talking up to 4 teaspoons of material found in every drum of new oil. So there is a lot of suspended particulate found in many oils. It doesn't fluctuate that much based on delivery method, whether it's bulk, tote, drum, pail, or even quart jug. The contamination levels are approximately in the same ballpark. So to help put that 18, 16, 13 into perspective, what I'm suggesting to you is this is 2, maybe 4 times cleaner than what we would normally expect in even the best handled new oils, and could be as much as 8 or even 16 times dirtier depending on storage of the drums or totes. So hopefully that helps put the ISO coding into a little bit better perspective in terms of where do the codes come from, what do the ranges mean, and sort of relatively how do you interpret one code from the next. Now saying this is ISO coding. ISO is but one method of reporting a particle count. There are in fact 2 other commonly used types of coding systems. One is called NAS 1638. It is rather archaic and hasn't been considered proper to use on any new pieces of equipment, but again, industry has many older pieces of equipment that when they were built, this was the de facto standard. So you may still see this in literature or within your own specifications. Now, a couple of key differences between ISO and NAS 1638 is NAS uses a 100 milliliter reporting system. So the particle count is per 100 milliliters, not per single milliliter. Another factor is it's what we call a differential count rather than a cumulative count. So instead of being from 1 micron size and everything larger, it has a definite end to the range. And the ranges are listed there on the left-hand side. We have 5 to 15, then 15 to 25, and so on and so forth. So with the NAS 1638 reporting system, it is very difficult to convert back and forth between ISO and NAS because the micron cutoffs are actually at different points. So you can approximate it, but there's no direct comparison. If you truly need an NAS 1638 particle count reported to you, you should ask the lab ahead of time so that they can set the instrument when it's doing its reading to properly report it, rather than try and convert an ISO count after the fact. The other method of reporting is by SAE. Now, SAE has two different ways of doing it. They can do a differential count, much like I just described NAS, or they can do a cumulative count, like the ISO 4406 method. But in both cases, they still use the 100 milliliter sample, so that sounds like NAS, but they use different classes, different numbering systems. So just to complicate things a little bit, you've got three different ways of viewing exactly the same result, and they don't cross-compare very well. Now, you can convert back and forth between an NAS and an SAE, but you cannot, like I said, convert back to an ISO, whether it's to an NAS or an SAE. So saying all that, we're talking about how the numbers are reported. We haven't talked about how to interpret them. What causes your particle count to go up most commonly? Contamination, obviously. You've got particles in your oil. So how do particles get in? Basically, any way they can. They will find their way through every opening, whether it's a dipstick, a hatch, a cover, a fill cap, breathers, you name it. They will also enter the oil through the use of any contaminated handling mechanisms. So whether it's a dirty funnel, pail, fill jug, anything like that will always lead to an increase in particle count. But one of the things I do like to stress is, as I mentioned, new oil tends to be at least about 8 times dirtier than is commonly required as an upper limit in most operating systems. So the mere fact you add new oil can increase the particle count, even if you're doing everything properly, so long as you've not pre-filtered the oil. Now, why we're so concerned about this, and there's many different charts that you can view that would suggest something similar to what I'm showing you here, but the most common cause for, and the key word here is premature failures, tends to be contamination, and mostly particulate contamination. So this is why we are so focused on measuring particles and understanding if that value is increasing and just at what level it is increasing to. We know that the presence of hard particles tends to lead to higher wear rates. Higher wear rates tend to lead to earlier failures. But particle counting is just one method of encapsulating that value, but we should be aware that sometimes it's not always correct. One of the more common ways that we can get an incorrect high particle count is through poor sampling procedures. If the bottle is not rinsed, if the sample point is not flushed, if the sample point is not wiped before the oil comes out, all of these are methods in which extra particulate can get into the bottle that is being sent to the lab. And if the particulate is in the bottle, it's measured. It may not be in the system, but it will show up on the oil analysis report as anomalously high. Another way that you can get an exceptionally high particle count is when the filters in your system fail. Obviously, filters are there to remove particulate, but if they fail, if they go into bypass for any reason, then the particle count will no longer be held at its normal values. It won't decrease, and it will slowly start to increase. If the filter outright fails, blows apart like the picture here, then it may release particulate, and you will see an increase in particle count over time. But there's one other way that is relatively common to see fluctuations within particle count data that I'd like to speak to, and that is namely the sawtooth pattern that some people see over time, meaning that the results begin low, they start getting higher, 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 and then there's a drop-off, and then they're low again. And they go low, higher, 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 and then there's a drop-off, and they repeat this pattern over time. This type of pattern is typically seen in systems where there are filter changes throughout the life of the oil. And the presumption is that every time there is a filter change, the particle count should go down. What I'd like to suggest to you, though, and this is just from my experience, that in fact changing the filter sometimes causes the particle count to go up even further. And what I'm not suggesting, because this is commonly said but is not accurate, is that a new filter is less efficient than a used filter, and therefore this is expected. I don't want to endorse that statement. How I've seen particle counts go up after filter changes is mostly in the cartridge filter market rather than the spin-on filter market, and it's because of this. It's because of improper filter installation. Now, if you're familiar with a cartridge style filter, you'll know that they sit inside of housings. The oil flow in the housing is from the outside of the filter towards the center of the filter housing. The picture on the right is of a filter housing with the filter removed. So we're staring straight down all the way to the bottom of the filter housing. That reddish brown circle, sort of halfway in the radius there, is the seal on which the filter should be sitting. What you would see towards the outside of that reddish brown area is the dirty side of the filter, and everything on the inside of the reddish brown circle is considered the clean side of the filter. Now, when you remove a filter without having fully drained the housing, what happens is the oil has to displace itself to fill the void where the filter was. So when you pop that filter off the bottom of the filter housing, oil from both sides, clean and dirty, rush to fill that little void. Well, one thing I always like to mention about filtration is that filters may stop a lot of particulate, but they do not necessarily trap the particulate. And therefore, filter housings, especially if they've been in service for a number of years, will build up significant debris on the bottom of the filter housing on the dirty side of the filter. Now, this is not a bad thing. It's not harmful. But if you don't change the filter properly, what happens is, and this is what you're seeing in this picture, when you pop the filter off the bottom, all that particulate from the dirty side of the filter may migrate into the clean side of the filter. And therefore, when you install a new filter, what you're going to see initially is a jump in particle count, because now you've got all that particulate, especially large particulate, on the clean side of the filter that will have to take one ride through the system before it hits the filter and gets stopped again. The other issue, and this is the extreme case, which is in the picture here, you may have so much particulate that jumped across from dirty side to clean side that you're now affecting the filter's ability to seal on that bottom seal. And therefore, even though you install a filter and it feels firmly in place and you tightened it and it feels tight, in fact, you've got bypass along the bottom of the filter because you've got all that debris that will basically erode away as oil begins to flow, and you get a path of least resistance down at the bottom of the filter outside of the media, and you'll have full bypass within the filter. You won't know it. You'll only see it later once you start doing your particle counting or look at your differential pressure. So for this reason is why I like to point out that when we see the sawtooth pattern, we should really pay attention to what the particle count looks like both before and after the filter change. And if we see that the particle count continues to increase after a filter change, we should suggest cleaning of the housing and making sure that the seal is properly cleaned so that the new filter will, in fact, do its job properly. Now, the pitfalls with interpreting particle counts is we have to appreciate that where we take the sample also has a significant impact on the particle count. So if we don't always sample from a consistent location, we're probably not going to get a consistent particle count. But if we sample from any of the zones where the flow is much more laminar or even just a dead leg, chances are the particle count will be higher than if we sample from a live flowing area. We also need to appreciate that without proper flushing, we're not getting a representative view of what's going on inside the system. And again, that stagnant oil or any accumulation that may occur near the sampling point will probably skew the results higher. It almost never skews the results lower. One last comment about particle counting, and this is a big one, is that particle counting is 4 microns and up. For those of you who attended the webinar about wear metal analysis, you already know this, but for those of you just joining us, when it comes to elemental spectroscopy, those results are typically in the 0 to 5 micron range. What that means is that these two tests will not necessarily correlate. So when people see an increase in particle count and immediately look to the reports at the iron and silicon values, just trying to get a quick benchmark if it's more wear or more contamination, you might not see that correlation. We are measuring particles in different size ranges from each other. So while there is a small amount of overlap, and they do sometimes correlate, don't always count on it. So that's particle counting for you. Moving on to the water testing. Water testing is also done in two different methods, crackle test and Karl-Fischer titration. So let me talk about both, beginning with crackle test. In terms of its scope, it's a quick check to measure gross amounts of water. The significance of this test is it's basically a pre-check for doing a better test, like a Karl-Fischer titration. It's also a good way of screening to see if there's going to be any significant or adverse effects on some of the other testing, like viscosities, acid numbers, particle counts, particularly the optical particle count. Now, the basic principle of a crackle test is quite simple. Take a drop of oil, place it on a very hot surface. You look for bubbling, you listen for crackling. If both occur, the presumption is it must be water. But a common question that's a follow-up to this is, well, what's the detection limit of this test? And there is no straightforward answer. This is the best answer I can provide you. This is a study done on nearly 500 samples by the folks here at TestOil. And basically, as you read through the columns, what you'll see is the lowest positive result, meaning what was the lowest value that gave a positive crackle, and the values you're seeing there were measured by Karl-Fischer titration. And the next column, though, is what's the highest value, though, that achieved a negative crackle. So I don't want to focus on the lowest positive, because yes, that may be the lowest result we could possibly get a positive crackle on. Rather, I'd look over towards the highest negative and understand that any value under that particular concentration of water could possibly produce a negative result. Therefore, the level of detection is somewhere closer to the highest negative than it is the lowest positive. But, to be fair, it's somewhere within that range. But as you can see, though some literature may promise a 250 part per million detection limit, really you're looking at more like 500 to 1,000 before we start to be absolutely sure that a positive crackle in fact means there's water, and a negative crackle in fact means there's not significant amounts of water. The only interference to this test is anything else that might cause bubbling. It won't cause the crackling noise, but anything else that might bubble, volatile things like fuels, solvents, refrigerants, those can definitely skew the interpretation of a crackle test. Now, the other way of measuring water is by Karl-Fischer titration. And according to ASTM, it is accurate down to 10 parts per million, all the way up to 25%. Truth be told, it is used at values much higher than 25% water. And for those of you questioning who in the world would run a system with more than 25% water in it, well, there are different types of oils out there, some of which are water glycols, which are meant to have approximately 50% water content. And in the metalworking industry, we even have some water and oil and water emulsions that range from 5% water to 95% water. So Karl-Fischer is typically used on all those, even though by its scope, it's meant to measure water more in the lower concentrations. The significance of measuring water and quantifying water is understanding if the water contamination is actually getting worse, if we should expect more contamination showing up on particle counts, if we should expect more oxidation of metals, so on and so forth. Now, the basic principle of the Karl-Fischer is it is a titration. If you remember your high school chemistry, it is a reaction where you're basically trying to neutralize an acid with a base, would be a common titration that you would have done. But in this case, what we're trying to do is react out the water. So we use a hydroreactive chemical, and we measure how much of it we have to add to the system before it stops reacting, and that's how we know how much water we've reacted out of the sample. Quick little trivia point there is water is the #1 cause of diesel engine oil related failures. It's the #2 cause in industrial equipment. If you're curious what #1 in industrial equipment is, it's particulate. So back to the particle counts. Now, the limitations to a Karl-Fischer is it can't tell you what kind of water you have, meaning it can't tell you what phase it's in, nor what source it's from. So it doesn't know if it's dissolved, free, or emulsified water, and it can't tell you if it's processed, fresh water, or seawater, salt water kind of things. It just says it's water. So if you're looking to figure out where the water is coming from and you have more than one possible source, you might have rain or condensation, but you also might have a cooling system with water or a water-based liquid in it. It can't tell you that. It can only tell you how much. The only interferences to this test, which are rather ironic given its sources, when German chemist Karl-Fischer created this reaction, he was actually trying to measure water content in sulfur products. But as we now know, sulfur actually skews the result a little bit. So if we have samples taken from sour systems, where there is, as an example, a compressor pushing some sour gas, or if it is a natural gas engine that's being fueled with a sour gas. If there's residual or extra sulfur within the system, it may skew the results a little bit. It's a known interference to ASTM. Now, saying all that, the repeatability and reproducibility of the Carl-Fisher test is produced here. It's a bit of a goofy formula with an exponent that's a decimal. So this is not math most people can do in their heads. So I've given you a quick quantification for 0.1 to 1% water content, showing you what the range works out to be approximately. So you can see that this is at least got a 10% variance on it in the minimum, and it escalates to more than 50% variance at some of the higher levels. So when it comes to water content, we probably shouldn't nitpick very small changes. The point is, you have water in your system. Water is never a good thing. Corrective actions need to be taken. You can't really worry too much about the decimal points on the water value. So the most common cause for your Carl-Fisher results to go up is obviously water contamination. Now, where did the water come from? Much like particulate, just about any way it can. Most oils are what we refer to as hygroscopic, meaning they absorb the moisture and will hold on to it. And the moisture can come from any path. Again, I list off caps, dipsticks, breathers, hatches, you name it. If it can breathe, then the moisture can come into contact with the oil. If it does, the oil will act like a bit of a sponge and hold on to it. Another source of water, though, is if we know we have a cooling system. If we have a cooling system, generally speaking, we use a water-based fluid on one side and we'll have our lubricant on the other side. If any of those cooling tubes begin to leak, or if there's any seals in between both systems and they begin to fail, then water, of course, will migrate over to the oil side. The water may be pressurized in some systems, so that generally speaking, the water always migrates to the oil rather than the oil migrates to the water. But some systems are more balanced and you'll get a little bit of both happening. So it's always important to understand what possible sources you have for water and what follow-up actions you can do to confirm if one's more logical than another. Quick way of doing that is to look into your cooling system if it's got a reservoir of any kind and see if you've got oil floating in there. If you do, then clearly you've got a two-way leak. Another way to suppose it could be happening is what happens if you've got an increase in acid number. If you've got an increase in acid number that seems to be outpacing normal increases, you're probably forming acids at a faster rate due to water content. And the water content getting in there may cause the acids to dissociate a bit faster. But funnily enough, if you are boiling off the water through whatever ventilation you have in the system, you might not see an overall change in water content, but you will still see that change in acid number. If it becomes significant enough, you may actually even see an increase in viscosity. So a couple of the exceptions. We should accept the fact, like we said, new oil is not clean oil. New oil is also not dry oil. All oil tends to have some water content to begin with. So we should appreciate that every time we add new oil, we may be injecting a little bit of extra water, and that under normal operating conditions, that water content may in fact be lower. The other aspect, much like particle counting, is where or how we take the sample. Again, we want to avoid all those dead legs, especially if they happen to be low points, and we don't want to take samples once oil has cooled off, because water begins to condense and separate out, and these low points will collect it. And if we sample from there without proper flushing, we will get extraordinarily high water content appearing in the sample that will seem rather relatively anomalous compared to the previous trend. I've had instances where I've seen samples come in that were reported at upwards of 99% water, meaning pretty much the entire bottle is water. And the suspicion on our end is simply that that was a sample taken from a low point and they did not absolutely flush it at all. And basically the first 4 ounces that came out was what was collected in the bottle. Now the pitfalls with water testing, a little more focus on crackle here because crackle's got greater pitfalls. Negative crackle does not mean it is dry oil. Doesn't mean there's no water. Simply means it's below the detection limits for the test, which, as I showed you, vary according to the oil type. The other side of the equation, though, is A positive crackle doesn't really give you any ideas to the severity of how positive it is, right? Both those samples you see in that picture measured out at a positive crackle, meaning that they bubbled and crackled when they hit the hot plate. Clearly, the sample on the left is far more contaminated than the sample on the right. But those who rely on crackle test only wouldn't know the difference. Thankfully, this is why we always follow up every positive crackle with a Carl Fisher and give you a quantity, because we don't like reporting positive crackles. But just be aware of that if you are doing your own form of crackle test or using a lab that only reports crackle. So saying that, that's everything about water. The last couple tests I have to talk to you are going to talk about wear. I'll begin with the ferrous wear concentration very briefly, and then I'll get into analytical ferrography. Ferrous wear concentration is kind of like the crackle test of the wear debris. It is meant as a quick check of ferromagnetic particles. The significance of this check is it's used as a good screen and may suggest the performance of a better test, namely analytical ferrography. The basic principle of this test, when we do ferrous wear concentration, this should not be confused with PQ index or particle quantifying index. It is a little bit different than that. With ferrous wear or PQ, essentially you need two magnetic coils. One is a reference, one is a measuring coil. The idea behind both tests is you bring the sample into play with the one coil and it measures the difference in how its magnetic flux has been altered compared to the reference coil and can quantify the amount of debris that is there. In this version, in the ferrous wear concentration, the sample is placed into a syringe. The syringe is placed directly within the magnetic flux coil. So in this case, we're absolutely interrupting the magnetic flux by intersecting with it. And the nice thing about this instrument, it reports the value as a part per million. So it's a number you can actually understand and do something with. It's a concentration that makes some sense. A PQ index, just so you're aware that though the instruments look similar, how it performs a measurement and how it reports it is radically different. With PQ index, you do not insert the sample into the magnetic coil, you place it on top of one. Basically, you turn the bottle upside down and let the oil flow to the cap, and it measures the magnetic flux through the cap of the oil sample. So depending on how thick the oil is and how well distributed the particles are, you can vary the results in a PQ index with quite a bit of error. The other thing is that a PQ index is not reported in parts per million. It's reported in its own internal index, which is not necessarily an intuitive 0 to 100 scale. So please don't confuse these two tests, even though they're both magnetometer based. Ferrous wear concentration is actually a part per million value. Now the limitations to this test, because it is not limited on particle size, which is a good thing, does make it unable to be correlated with elemental spectroscopy, which is limited on particle size. So the basic assumption then becomes, well, how are they correlating? If your elemental spectroscopy is high and your ferrous wear concentration is low, then the assumption is that the particles that are being created are normal, and this would be expected. If both values are high, then it's transitioning from normal to abnormal, and if elemental spectroscopy is low and only ferrous wear concentration is high, then you know all your particles are of a critical size. So the correlation between these two, though it doesn't correlate directly, how it correlates does tell us some information as to the severity of the results. In terms of interferences, it is a common misconception that this type of testing only measures iron particles. It does measure anything ferromagnetic, and both cobalt and chromium are ferromagnetic. So if there's substantial amounts of either of those elements present in the oil sample, then they would of course skew the results a little bit. Cobalt is rarely seen, so that's not too much of a concern, but chromium is quite possible in any coated parts. It would also be possible in any system that's got stainless steel, if the stainless steel is prone to wear either by erosion or other mechanisms. So like I said, this is kind of your crackle test of the wear debris. It's a good screening tool. It suggests that maybe a better test should be performed. The better test that should be performed is analytical ferrography. What this does is it uses a microscope and an analyst, a human, to identify, based on morphology, shape and size of particles, what type of wear mechanism and what type of material. This is about the most forensic type test you would ever see in a commercial oil analysis lab. So if you watch a little too much CSI and you think that all labs look like how CSI labs operate, well, commercial oil analysis labs don't really look like that. And most of the testing they do isn't even remotely close to the level of depth that you would see in some of the reveals that they do on that show. This test is the closest. Now the significance of this test is if we understand the morphology of the particles, we understand based on its shape and size what wear mechanism created it and how severe that wear mechanism is, we have a pretty good idea on how that system is operating and how severely it may be wearing. Now the basic principle of this test can be done one of two ways. The first way is done using a ferrogram, as we call it. Most people just refer to it as a slide. It's a glass slide in which we allow oil to flow down the slide. Now when oil flows down the slide, basically at the top is higher and at the bottom is lower. So the oil is flowing towards us there. The particles will separate out from largest to smallest. Now I know at first glance you're going to say to me that, well, particles would never orient themselves as well as are shown in that picture. And that's because, no, normally under fluid dynamics, particles will settle out largest to smallest. However, they don't align themselves unless we use magnets. And there are a series of magnets placed underneath the slide to encourage this sorting and orientation. So all the ferromagnetic particles will sort out in nice straight lines, as you see there, and all the non-magnetic particles will randomly distribute across the slide. Once the slide is prepared, it is able to be analyzed under the microscope by an analyst, and if you want, it can also be subjected to 3 heat treatment ranges, whereby we inspect the slide once, then we heat treat it at one temperature, and some of the metals may change color, some of the metals may even melt. And we reanalyze it again under the microscope, and then we can repeat this 2 more times at increasingly higher temperatures. So this provides us with a pretty good view of all the particles, helps sort them according to size, which makes quantifying them a bit more defined. The faster way of doing the test, though, is to simply do a patch test. So if you run a sample through a membrane patch filter, like you see here on the right, the particles distribute absolutely randomly all over the place, but you can throw this under the microscope and get a pretty good view of all the types of shapes and sizes of particles. It's just not quite as easy to overly quantify them, and of course once it's on a membrane patch we can't run it through the heat treatment sequences that you might want. But either way can be done. Both are given the same protocols in terms of how the particles are identified and sized. So with this, we should appreciate that in terms of limitations to the test, there is no particle size limitation. Doesn't matter as long as it appears on the slide of the patch, you can see it. But that the test is strictly qualitative. You can't really rely on it to be 100% quantitative because it is being measured subjectively by a human looking at what's distributed across what they're looking at under the microscope. But saying that, it doesn't have any interferences, which is good, but there can't really be much of a precision or a bias statement because it is such a subjective test. So to try and remove some of the subjectivity to the measurement, we try and use a fairly standardized method of reporting, and thankfully again ASTM comes to our rescue for that. So here are the different categories as reported by ASTM. Rubbing wear is largely considered to be normal type of wear. These are the type of particles we would expect to find, and as long as they are small in size, aren't considered much of an issue. Rolling contact fatigue, on the other hand, are particles that have already been created as wear particles, but may have been contributing to further wear by being reintroduced into the system, or may be evidence of significant fatigue in a rolling element type bearing. So particles in this category tend to be considered less normal. Once we get into cutting wear, however, these are particles that are generated by 3-body abrasion. These are never considered normal, and this is definitely considered severe wear. And these are basically the 3 categories of wear that you would look at, sort of the normal, transitioning from normal, and absolutely abnormal. But if there's a particle that doesn't fit any of these 3 categories, and I kid you not, this is directly from ASTM, they're referred to as chunks. One of the least scientific terms you might ever see on a report, but it is in fact a well-defined category to identify particles that simply don't fit the other definitions. We also go on to identify anything spherical. Spherical is an indication of a different type of spall that might form. It is also an indication of debris left over from manufacturing. So under a microscope, we can see these and we can identify them based on their overall shape and color as to what is the likeliest mechanism that created them there. It's important to note that sometimes these spheres are caused by stray electrical charge. So there is a bit of an outside factor there that would be considered absolutely abnormal, but also not that common. When it comes to the particles that don't seem to be created by physical wear, we've got a few other ones here. We've got corrosive wear debris, which is suggesting a chemical reaction has caused the wear particles to be there. And then we have dark and red oxides. Now, a red oxide is simply a fancy way of saying rust, so that's pretty straightforward. But the dark metallic oxides are particles caused by welding. And when we say welding, we don't mean that maybe you've been welding near the component or it's debris from when the piping was welded together. But it's when the two surfaces in relative motion to each other come under such extreme pressure and contact that they temporarily weld to each other. And as they pull away, what happens is that particles get basically smeared off one surface to the other or pulled from one surface to the other, have a very distinct and dark appearance. And in these cases, these particles typically are caused by a lack of lubrication, whether it's an oil flow, like a volume issue, or it's a viscosity that's way too thin. But this high heat and physical wear combined together create a very distinct type of particle. The remaining categories, we have one for dust and dirt, just to identify anything that's not a metal but is crystalline in appearance. So it could be sand, it could be dirt. And then there's an other contaminants category, which is basically your catch-all category to help identify anything that didn't fit all the previous categories. So this is where you would identify things like paint flecks, fibers, whether they be from coveralls, from lint-free rags, from filters. If you see seal material, anything like that, that would suggest that this is not metallic and not necessarily an airborne contaminant, but something largely generated internally. One extra definition that we have out there for a field that we record is oxidation byproducts. So basically a way of saying the soft particle, the varnishes. If we see any of these on the slide or the patch, we will identify those separately to help give you an idea, because again, we've got an expert looking at this under a microscope. We might as well point out anything and everything that we can, but we don't like to leave this one falling into the other contaminants category because there's way too many other things that are in there. Now, the basic principle of interpreting all of these categories is obviously you don't like to see anything beyond the normal rubbing wear present on any sample, but it should be expected that, of course, the dust and dirt will predominantly always appear. There will almost always be something within this category. So the two factors we look at when we're interpreting analytical ferrography is both what is present in terms of if it even shows up on the report, how much of it is present, obviously is corollary to that, but then the size is the other side of it. As long as the particles, though they may be abnormal by definition, as long as they're small and the quantities are low, this is not considered to be much of an issue. When the quantities go up, and especially if the size goes up, this helps indicate the level of severity towards whatever mechanism is creating them, and obviously that would be interpreted with a much greater urgency. So with that, that concludes the instructional portion of the webinar. I will now take a look over at the questions, because I do believe at least one has been posed. So let me pull that up and I'll answer any questions that have been given here. If you do have any questions, please use the question toolbar and continue asking questions while I answer these ones. So the question I am seeing is from Juan. He says, is water related with oxidation? To a point. Understand oxidation itself is a reaction with oxygen. Oxidation tends to be increased in terms of how fast it happens by factors like temperature and water content. Water is a pretty good catalyst helping the reaction. especially when we have dissimilar metals. So yes, if you have an increase in water content, you will expect an increase in oxidation, and the higher the temperature, the faster that will occur. The common equation that's usually given to you is Arrhenius's equation. Arrhenius was a chemist who discovered every reaction in nature doubled with every 10 degrees Celsius, 18 degree Fahrenheit rise in temperature. And this tends to be significant when we're dealing with temperatures over about 70 degrees Celsius, 160 degrees Fahrenheit, that rate of reaction becomes much more significant, noticeable. At these temperatures, if we have extra water content, then what we'll do is we'll see faster rate of acid production. And one of the ways we help define if this is a possibility before it happens is the value of hydrolytic stability. And hydrolytic stability is a test that's performed under a higher water concentration to see how quickly acids will form and at what level they will basically take off, exponentially increase. So yes, water will definitely affect oxidation. All right, my second question that I see here is from Sylvia. It says, what an equal ISO class like 16-16-16 could mean? I'll try and give you as thorough of an answer as possible to that question because there's two ways to interpret this one. If your particle count was truly 16-16-16, meaning at those levels, not that they're all equal, typically what that indicates is that all the particles present are larger than 14 microns and you've got no particles smaller than 14 microns down to 4 microns. That it would be pretty rare. That would be a very odd occurrence if that was to happen. Normally when we see all the ISO codes equal, they tend to be at very high values like 23 or 24 kind of values, maybe even as high as 27 for that matters. What that typically indicates is you've maxed out the instrument that's performing the measurement. That basically all the classes, all the codes are as high as are possibly able to be measured. And that's where more commonly I see all the codes being equal, the 4, 6, and 14, all the same value. But if they were truly at that 16-16-16 level, it would indicate all the particles are larger than 14 and there are no particles in the, or no significant amount of particles in the 4 to 6, 6 to 14 range. Okay, my next question says, if particle counts are only worried about particles greater than 4 microns, why do elemental spectroscopy for particles 0 to 5 microns? So I'm guessing, okay, the question is, why do we do particle count in one range and elemental spectroscopy in the other range? I would encourage you to download the webinar that we did for wear metals, but the explanation that I gave in there is the 0 to 5 micron range tends to cover all the normal wear metals in terms of normal sized particulate generated under normal wear modes under normal conditions. And normal airborne particulate is in the 0 to 5 micron range. So we measured the normal contaminants, again expected under normal conditions. And all the additives are submicron. So those are all easily captured, those 3 different aspects within elemental spectroscopy. What elemental spectroscopy does not measure very well is the abnormal, when the wear modes get much more severe, when the level of contamination gets much higher than is typical. And this is why we suggest all these different tests. Again, there's no one test that measures everything. If there is, we wouldn't offer so many other tests. So analytical ferrography is a good way of encapsulating values experienced in abnormal wear modes as well as the normal wear modes. Particle counting is a way of encapsulating all the abnormal contamination compared to just the normal levels. So that's why you would measure the 2 different ranges and why they don't overlap perfectly. The next question I have here is from Carmen. It says, do you have experience with Carl Fisher oven method? Yes, that is the method that we prefer to run. We do the ASTM 6304 procedure C, the oven method, where you heat the sample, and instead of injecting the liquid directly, we're heating the sample and taking the vapor that's coming off and throwing it in there. I think there's a bit of a follow-up typing here to the 16-16-16 ISO question because it's providing me just the data. But the next what looks like question here says, we have problems to determine the water content in transmission oils. Is it sticking the generator? Do we have to perform a special treatment to avoid it to stick to the generator? Transmission fluids, there's nothing really terribly unique about a transmission fluid. It shouldn't cause you any different issues than a standard hydraulic or engine oil when it comes to measuring in a Carl Fisher titrator. People tend to only have issues when it comes to the really thick oils, like gear oils. If you've got something that appears to be building up on the generator, then the only thing I would suggest in my experience is to have backup generators, clean ones, and anytime you run one of these samples, once you do your quick QC check, run only that sample and no other samples, and then let it go through a thorough cleaning procedure afterwards. So basically I'm saying treat it kind of special. I've not had that much experience with significant contamination within the instrument. So if you're experiencing that, then I would say that's probably not that normal, and there's got to be something else going on in there. So you can double check your solvents, which I'm sure you've already gone down that path, but ensure you're using the correct solvents to help dilute the sample as it enters the reaction vessel, as long as that's okay. Like I said, I wouldn't expect a transmission fluid to have any issue. The next question here is from Brandon. He says, is there a correlation between submicron, less than 4 particles, and varnish? There is to a point. This is why when we do a varnish report, we actually perform particle counting by both the optical and the pore block method, and then subtract one from the other. Basically what we're suggesting, which is a bit of an assumption, is that if the particle count is substantially higher optically than it is through pore block, then the difference between the two particle counting methods is suggestive that they're soft particles, and that would be, of course, indications of higher level of potential insolubles in the oil. And the higher the level of insolubles, generally speaking, the more varnish we expect to be plated out. But Brandon, do appreciate that if you can measure it in the bottle, it means it's in the oil. And if it's in the oil, it means it's not necessarily on the equipment. So even if you see a high particle count, it might not equate to high varnish, because varnish is what you call the plated form of the insolubles. The insolubles, as they're suspended in the fluid, are just generally referred to as varnish precursors or insolubles. So measuring high quantities of one doesn't always mean you're going to see a lot somewhere else. The common analogy I like to give is like describing water. Water can be rain or water can be a puddle. You can't have a puddle without rain, but you can have rain without a puddle. Rain is the insolubles, puddles is the varnish. Right? Just because it got a lot of rain doesn't mean I have a lot of puddles. It depends on how fast the rain falls and where it falls, and way too many variables. So always keep that in mind, that just because you see an increase in particle count doesn't mean you'll directly see an increase in the amount of varnish plated out on the system. You'll just see more in the fluid that could plate out. Next question, again from Warren. Is it useful to direct reading ferrography? Well, understand direct reading ferrography is not a whole lot different than ferrous wear concentration. It's a similar magnetometer-based test. The only difference is it classifies large versus small, which is a rough estimation anyways. So it's a good screening tool. It's a good trending tool. It's a quick pass without getting into something complicated like in analytical ferrography. But no, it's not a significant test. I mean, that's why it's substantially cheaper at most commercial labs to get a DR ferrography than it is to get an analytical. But like I said, it's not a whole lot different than ferrous wear concentration. The reason I like ferrous wear concentration so much is, like I said, it's a ppm value, not arbitrary severities or ranges. So with that, I think I'm just doing a quick check here that I've answered all the questions that have been posted, but by all means, if you have any further questions, my email is on screen there, and you can certainly contact me and ask other questions. I have seen one more question here that I will answer, and then I'll turn it over to Taylor. So the last question I'll answer at this time is one from Namrata that says, does the oil viscosity have any implication if we want to do particle count in oils? It indicates that she's left the webinar, so she's not going to hear this answer, but it is a good question. When it comes to particle counting, the viscosity of the oils does play a role depending on the type of particle counter that you have. If you're using a pressure system to push the sample through the sensor versus if you're using a positive displacement like a syringe drive, it has a significant impact in the accuracy of the particle count. If you are using syringe drive, it's usually not much of an issue because you will get constant flow. The downside is the thicker the oil, the more likely it is to have air bubbles entrained within the fluid, which will count as particles, which tends to skew the results higher. And again, is why, as I said, people like to dilute the samples and negate most of those effects. So if you're going to dilute your samples, then at that point, viscosity is no longer an issue, and you can remove all those problems. So there we have it. Taylor, thank you so much. I'll let you wrap up.
All right. I would like to thank everyone for joining us today, and thank you very much, Evan, for presenting, and everyone have a great rest of your day.